reference intervals usually are quite important, particularly from the point of view of interpretation of laboratory results. When you look at it, we, particularly in clinical chemistry, produce a lot of data from blood, from urine, from any of these other biological fluids, CSF, acetic fluid, amniotic fluid, so CSF included. So the results we usually get are usually values, and sometimes they are completely meaningless. So what we need to do is to figure out the value we obtain is set within certain limits obtained from a healthy population. Remember, health is a relative concept. And what you sometimes think today, now is healthy, it may not actually be. Statistically, what we do is that we get that population, or the majority of the population, 95% of that, which is the mean plus or minus 2 SD. You remember we went through the biostatistics, and we said that from the mean in the middle, you go to the side, one standard deviation, both sides, mean plus or minus 1 SD. That will contain 68.2% of your data. Keep on moving away from the mean, 2 standard deviation on both sides, mean plus or minus 2 SD. And that will give you, or rather, that area will contain 95% of your data. These are called confidence intervals. And this particular confidence interval, the mean plus or minus 2 SD, is the one we use to set up our reference intervals. In other words, what we are saying is that if you are dealing with the normal population, then that parameter will be in about 95% of the population, or it will range between this value and this value in 95% of the population. The other 5%, which is 1 out of 20, will be outside those two limits by chance alone. That does not mean that that one person is abnormal. But what it actually means is that that person requires further investigation as far as the parameter is concerned. When I'm talking about these parameters, I'm talking of sodium, I'm talking potassium. Potassium, the reference interval is 3.5 to 4.5, and that is the 95% confidence interval. That person who is going to have a value of 3 millimoles per liter will be hypokalemic, or supposedly hypokalemic. That one who has got above 4.5, say 5 millimoles per liter, will be hyperkalemic, or supposedly so. It does not mean that that person is hypokalemic or hyperkalemic, but we require to further investigate that 1 in 20 persons. Now, we must understand one thing. When we talk of reference intervals, or the interpretation of data based on that, we must understand that 80% of clinical decisions by physicians is usually based on laboratory results. So it's quite important that we be able to have reliable, accurate, and precise reference intervals. Now, according to the ISO standard, which is 15189, which is actually based on clinical chemistry, and there is a section on medical laboratories requirements for quality and competence. Paragraph 3.4 of this ISO 15189 describes the term biological reference interval. And they argue that this standard requires documentation and regular verification. It just shows you how important these reference intervals are. Now, a patient who is going to have a glucose of 11.8 based on the reference intervals which are incorrect will get that patient to go on to insulin, because the justification here is that the value is outside the reference interval and therefore the patient is diabetic. But this is based on 40 interpretation, based on 40 reference intervals. So you can imagine you put a patient who is normoglycemic on insulin because of suspected diabetes mellitus. So it's important for us to remember that. So again, I'll say that we need a lower and an upper reference interval limit. And that is usually described by the 95% reference interval of measured values. These values are obtained from samples of healthy reference group who are actually non-pathological with respect to the measurand. The measurand here is the parameter of interest, whether sodium, whether potassium, whether creatinine, or whatever. Now, as a convention, 2.5% of the values are below and above the reference interval limits. Remember, you have got a Gaussian distribution, a bell-shaped curve. You have got your mean plus or minus 2SD contains 95% of the measurand. Then on one tail, which is 2.5%, that will be the lower limit. The 2.5% on the other side will be on the upper limit. So that 5% is the one I'm talking about as 1 out of 20. All that you need to do is to divide 5 over 100, multiplied by 100. And that gives you 1 out of 20. Now, we need to know how to now set up this 95% confidence interval. Now, a problem has been that when we are setting up the reference ranges, or we want to do so, which is a requirement, by the way, WHO insists on the same. IFCC, which is the International Federation of Clinical Chemistry, also requires that to be done, and all the other clinical chemistry forums all over the world, they require you to have credible reference intervals. Now, some people usually call these guide limits, or GL, because we talk of reference intervals we talk of reference ranges, we talk of expected values, and before that, it used to be normal ranges. Normal ranges was discouraged in 1966 by Grasbeck and Sellis, who noticed that there was a misunderstanding. The term is actually a misnomer. What you call normal ranges, or the word normal itself, could mean habitual, it could mean ideal, it could mean average, it could mean a normal distribution with all those mathematical variables associated with that. So what they recommended was the use of the term reference interval, or reference range. Now, when you use the term reference, the question which comes up is reference to what? It will be reference to age, it will be reference to gender, it will be reference to the ABO blood grouping or whatever. So it forces you to qualify the term, reference to what? And that's how the term normal ranges was killed and buried in 1966. So this term, these guide limits are usually taken from package inserts of in vitro diagnostics, what we call IVD. If you go to most of the laboratories in the hospital where they are measuring parameters, you go to either laboratory 6 in KNH, or you go to the clinical chemistry unit, what you find is that these days nobody is actually making reagents. What they are doing is they buy kits. And in these kits, each one of them, whether it's for cortisol, for creatinine, it's for HIAA, or whatever other parameter which is being measured, there is a package insert which describes the test, and it also gives you the manufacturer's reference interval. Other laboratories will go to literature, they go to the library, you check for the reference interval set up by other laboratories outside there, and they use that as their reference interval. If I measure a parameter and then I give you that parameter, no reference range, that one is of no diagnostic value. It is of no medical value. It must have a reference interval next to it in brackets, indicating the method which was used to set up this reference interval is this and this. So it is always important to do this. Now, incidentally, most of the IVDs, or the in vitro diagnostic manufacturers, are starting to insist on laboratories setting up their own reference intervals. One of the problems we have with this is that the cost of doing reference intervals for parameters is usually time intensive. It's also cost intensive. And for some of the laboratories, it's actually out of reach. So what has happened is that over the years, people have been using reference intervals. You do not know even where they came from. The time I've been in the KNH, which is quite a number of years, I cannot figure out when I saw a reference interval determination being done. I would probably think I was involved in one of the reference interval for steroids, which was being done by Deborah Shaw for obs and gynae. Outside that, the only other one I remember, we did it in somewhere in Canada, in Manitoba, where we are setting up reference intervals for urinary albumin estimation. What we were doing before is that we were measuring albumin in urine using the method used in measuring albumin in blood, which is called BCG, or bromocresol green. The problem with bromocresol green is that when you use it in urine, they are what are known as middle molecular weight compounds, which usually interact with BCG, and you get false positives. So what they were introducing was what is called use of bromocresol purple, or BCP, in the measurement of glucose or of albumin in urine, because the assumption was that there was very little interaction between BCP and the middle molecular weight compounds. So less false negative, positives. Outside that, I cannot remember of any other. What we have been using is sodium 3.5 to 4.5, potassium, sodium 135 to 145, potassium 3.5 to 4.5 to 4.5, calcium 2.1, 2.6. But I have never seen that one done. The requirement is that if you have been using a particular reference interval, either from a manufacturer or it has been in use for a long time, and changes have happened in the measurement method, then you need verification. And verification is easy because all that you need is about 20 males and 20 females, and you can do that. Problem is, like I said, we do not have time to do that. We think what we have been using for the last 20, 30 years is still valid, which is not correct. Now, let's now go to how do we set up reference ranges of a particular parameter. The first thing we must understand is that whatever parameter we want to set up reference interval for is already in plasma in healthy subjects. Sodium, when we say 3.5 to 4.5, that is in 95% of the population. That other 5%, which is outside the limits by chance alone, that is statistical. And like we said, anybody who is outside those limits requires further investigation. So what we need to do is to go into the general population and we obtain what is called a reference population. A reference population is obtained from the general population, and it should have the characteristics of the general population, demographically and otherwise. Remember, whatever information we are going to get is going to be used to manage or treat those people in the general population. So these people should be a subset of that general population. So you could go in with an inclusion-exclusion criteria to obtain your reference population. Those are subjects who are healthy. The exclusion criteria, based on the Scandinavian Society for Determination of Reference Ranges, is that anybody who is on any type of disease should be excluded from the study. Anybody on medication, any subject on medication for any type of disease, that is an exclusion criteria. These key factors like hypertension, diabetes mellitus, compound genetic problems, all these are also exclusion criteria. Subjects who are on oral contraceptives, who are smokers, smoking or use of tobacco, it could be chewing, could be sniffing, it could be smoking. The effect is the same. Now, the other thing to look at is the physiological status of the patient. Look at the reference interval for glucose. We talk of random glucose with its reference interval. We talk of fasting glucose. So that physiological status is also important. We must identify what physiological status the subject is in. Pregnancy is usually regarded as an exclusion criteria. But this does not mean we cannot set reference intervals in pregnant patients. What we need to do is to set up reference intervals based on each of the trimester, either first, second, or third. Sometimes we may need to set up reference intervals in the pediatric population because we know children are not small adults. And sometimes parameters will actually vary. So we need to set up reference intervals for a pediatric population, for a geriatric population. These are actually important issues. Now, when we then obtain our reference population, we could probably be looking at the reference interval for potassium in the student community. And we come up with about 1,000 persons who are eligible because they are apparently healthy in quotes. Now, one problem, just like I have mentioned before, is that setting up reference intervals is an expensive process. An example here is setting up reference intervals for TSH, thyroid stimulating hormone. A kit for TSH for 50 tests will set you back about 21K. And that is not actually 50 tests. If you are a charging laboratory, the actual number of tests, patient samples you can do is about 35. The other 15 will be used to support the other 35 in terms of calibrants, in terms of standards, in terms of controls. So remember those ones you can charge. So if you have got 1,000 subjects, that's going to be quite expensive, because now you'll be looking at maybe the 35 you divide by 1,000, then you find the number of kits which you're going to use. So we need then to have an acceptable number in terms of statistics and in terms of the costing. From the statistical point of view, you would need a number of subjects who will give you enough statistical power for the validity of your reference interval. And the way we do this is to use what is known as Fisher's equation. Fisher's equation is that's F-I-S-C-H-E-R. Fisher's equation is a general equation, and it has been used in the medical school for many, many years. And most of the studies which are usually done by postgraduate, because they are usually the ones who are paying, or they are the ones who are supporting their projects, they have got to use this equation. Now, this equation usually is to calculate the number of individuals who fit that statistical requirement. So it's usually N, that's the number of observations, as we usually say, or the sample size, is equal to Z square. For those people who use the C, is actually Z, but I love Z because I've never known what to call the other one, the other C, the one which looks like a half moon. This is Z square P, opening bracket, 1 minus P, closing bracket, all divided by D square. Again, the sample size N, capital N, is equal to Z square P, opening bracket, 1 minus P divided by D square. Now Z, I keep on saying mean plus or minus 2SD. 2SD is actually 1.96, all rounded to 2. 1.96, we round it up to 2. So we talk of 2 standard deviations, but it's actually 1.96. So in this case, it's 1.96 squared. P is the preference of the condition. Remember, I said this is a general equation. And this would now be the proportion of the number of people you need from that sample size. A good example here is a new drug which came up to treat maybe corona or even malaria. And the first thing you would actually, you want to look at the efficacy. The thing you need to do is to go to an area where there is malaria and an endemic malaria region or county, and then you look at the number of subjects who have got malaria or patients who have got malaria, and you come up with a percentage. And if you find it's about 30%, maybe, that would probably be about 0.3. And then 1 minus P, that would be 1 minus 0.3, that gives you 0.7. Some people usually have it as Z square PQ, Q being 1 minus P. And then you divide that by D square, which is the precision which was used to obtain the preference P. And this one is usually provided for you is usually 0.05. So 0.05 squared. And if you key in your right numbers in there, you should get a good value like 200 out of the 1,000. Now the question comes in now. You have got 1,000 eligible subjects for the study, or there's a pool of 1,000 possible candidates for your study. And all that you need is 200. According to statistical theory, you cannot go in and say you, and you. You need to randomize the recruitment. so that you reduce bias. And the way you do this, you can go to your statistician and he's going to come up with all kinds of possibilities. But remember, it's also easy. All that you need to do is to probably even use a coin. The first person who comes in, you toss a coin. Heads, I include you. Tails, I don't. That is random enough. But another way you can actually do is to come up with what is called random numbers. You have small pieces of paper. Yes, 200. No, 800. So every one of those 1,000 persons, they pick a piece of paper. Whoever gets yes gets included in the study. Now, sometimes it doesn't work out all that smoothly. And what you might find yourself doing is to go back to the statistician, because most of the girls picked the yes, or most of the boys picked the yes. You want some kind of equity, and the statisticians usually have got ways of making you be able to sort out that problem. So eventually you end up with your 200 subjects. The next step is to correct specimen. One of the problems we have with setting up of reference intervals and the so-called guide limits is that sometimes you are not able to correct your specimens properly. And this has also been a problem even for collection of specimens for analysis. About 73% of the errors obtained in clinical laboratories, and particularly clinical chemistry, is that most of the errors usually originate from pre-analytical sample correction, or what we call pre-analytical errors. The preparation of the patient, the obtaining of the specimen, the transport of this patient, including use of the corrective tubing, either preservative, coagulant, either use the long anticoagulant, use the long preservative. A specimen was supposed to be frozen. It wasn't frozen. It was supposed to be transported in ice, maybe to maintain 4 degrees. It wasn't. The sample was corrected, and before transport, and this is quite common, it was corrected 8 in the morning. It was supposed to be in the lab within 1 hour. It's taken to the lab after 3, 4, 5 hours. At that time, there is deterioration, leakage of enzymes, leakage of parameters like potassium, magnesium into the cytoplasm. So what you are actually going to get is erroneous whatevers. Then the sample gets to the lab. It's most likely supposed to be separated, cells from serum plasma, but it wasn't. Again, further leakage. You look at glucose, the cells are still undergoing glycolysis, and they're utilizing glucose. maybe sodium fluoride was not added. Sodium fluoride usually is an inhibitor of the enzyme enolase. And as long as enolase is effective or is still functional and is within the cellular membrane, then glycolysis still continues. So the amount of glucose in the patient at that time when it was taken, it will be different. So in a nutshell, what I'm saying is proper methods should be used to correct the specimen. And again, remember that we are going to set up this reference interval for our parameter as a one-time reference interval. I just mentioned before, I've been there for years. I've never seen, I never even know where the 135, 145 for sodium came from. Neither do I know 3.5, 4.5 for potassium. So it must have been done many years earlier. So we need to have something credible we can stick on to for a long period of time. But if you're not comfortable, like I said, just pick 20 males, 20 females, and evaluate or verify what you think may be not very plausible. WHO keeps on sending brochures saying every laboratory must set up its own reference intervals. If you cannot verify what you are actually using. For most of the biochemical parameters, the rule of the thumb, even if you're not going to use the Fisher's equation, you should not use for a parameter which is new. Like you have come up with a new marker for coronavirus, for example, and you want to set up reference interval for this marker, then you have got to go to the population and measure the parameter in about 100, in not less than 120 subjects. For a parameter which is already done somewhere, you can find it in the literature. The rule of the thumb is that go for 40, 20 males, 20 females. So the specimen gets to the laboratory, and it's mandatory that the laboratory must use proper quality control methods to assay the parameter for the parameter. If it's a measurement equipment, it should have been surfaced, optics, power circuit boards, everything, so that it's in tip-top condition. I still keep on telling you that this is a one-time thing. So make sure whatever you are going to use is in tip-top condition. Then the laboratory is going to do the analysis for you. We have got 200 subjects. Who have got their potassium to be estimated. And if proper quality control methods are used, the laboratory is going to give you the results for potassium in millimoles per liter. What you're going to find is that most likely your values will range from maybe 3.9 to maybe 5.1. And in between, you have all the other values, 3.2, 4. Then you probably get as number 6, you get 5.9. And number 7, maybe you get 2.1. And number 8, you get 37. So what you need now is, according to statistical theory, the main requirement from here is to get rid of outliers in the data. Outliers are values which are discordant. Outliers are values which do not conform with the rest of the data. And it's quite easy. If you look at the data properly, I said number 8 was a 37. And you remember when you are the one who recruited these subjects, it was normal. And we know that 7 is not compatible with life. And you cannot remember sampling a cadaver at one point or the other. So what could have actually gone wrong with the 37? This is not even a critical value. If you verify the data properly, you find 37 was a 3.7 with a decimal point missing between 3 and 7. These are common in manual methods. They are called transcriptional errors, and they are easy to identify or very difficult to identify, because I'm looking at this data and I cannot expect a 37, so I'll be reading it as 3.07. Now, if you are not sure, pass it over to your friend, and he can go through it, and you probably point out that number 8 is a 3.7. If you can remove that, then you can calculate the mean for this data and the standard deviation. We know the ways we calculate the mean: the summation of all the values unified by the number of observation, which is 200. Then we go through variance and we obtain the square root of the variance, which will be the standard deviation. And if the 37 was removed and it's reading a 3.7, the chances are that our data will give us 3 or maybe 4.0 and millimoles per liter and 0.2 millimoles per liter as the standard deviation. Now the question comes in, is number 7, which is a 2.1 millimoles per liter, and number 6, a 5.9, are they outliers or not? Now, what you need to do now is to use what is known as Dixon's criteria, where any value which is outside the mean plus or minus 3 SD, which is the 99% confidence interval. So what you'll do is you look at number 7 is 2.1, and our mean is 4.0. If you multiply the standard deviation by 3, it gives you 0.6. And now we are looking at the mean plus or minus 2 SD. And 2.1 is actually on the lower side. So that would be mean minus 0.6. So 4.0, which is the mean, minus mean minus 2 standard deviations, which is 0.6, and that gives you 3.4. So 2.1 is below 3.4, which is the lower limit. Therefore, it's an outlier and it has got to be removed. Now, for the 5.9, now we shall look at the mean, which is 4.0 plus 0.6, and it gives you 4.6. And 5.9 is outside the upper limit, which is 4.6, and we have got 5.9. That's number 6, and that one also goes. So we have thrown out two values. 2.1 is an outlier. It's below mean plus or minus 3 SD. No, it's below mean minus 3 SD. And 5.9 is above mean plus 3 SD. So we are left with 198 data points. So now we recalculate the mean again. We have removed outliers as a requirement of statistical theory. So we are left with 198 parameters, and we recalculate the mean. So the mean here most likely is going to change to 3.8, and the standard deviation may not change so much. It will be still 0.2. So our reference interval now is the mean plus or minus 2 SD, which is a 95% confidence interval for our population of the student community. So what does this one translate into? It translates into the lower limit will be 0.2 times 2, which gives you 0.4. And we subtract from 3.8, and that will give you 3.4. That will be the lower limit for the student potassium levels. The upper limit is going to be mean plus twice the standard deviation, which will be 0.4 and plus 3.8, and that gives you 4.2. So for our student community in K&H, we are not going to use what we usually use, 3.5 to 4.5. We shall be using 3.4 to 4.2 as the reference interval for that group, for that community. At game short. So we have set up our reference interval for sodium, and you can set, for potassium, and you can do this repeatedly for every biochemical parameter you can think of, current and those new markers which are coming up for diseases and things like that. Now, I'll just mention one thing. For most of our biochemical parameters, they exhibit what is called a unimodal distribution. I mentioned that last year, meaning that if you sampled a large population enough for creatinine, what you'll find is that it will give you a Gaussian curve. It will give you a normal distribution, which is unimodal, bell-shaped curve. As long as the population is large enough. Now, a few times, what will happen is that you get parameters which do not follow this rule kabisa. And one of them is hemoglobin. When you go to hematology, you'll find when they give you reference intervals for hemoglobin, they have got two reference intervals, one for males and one for females. Because what has happened here is that if we take the measurements for hemoglobin in your class, where you've got boys and girls, what you get is not exactly a normal distribution, or you're not going to get that classic bell-shaped curve. What you get is two distributions in one. And what you need is to extrapolate one so that it comes out as a different distribution from the other one. So you'll have one distribution with a primary mean for females and one with a secondary mean for males. Males have got higher hemoglobin than females. So you get two curves in one, which is called a bimodal distribution. Now, when you get bimodal distributions, then you need to partition that data. And the partition criteria could be age, it could be gender. And in this case for hemoglobin, it's actually gender. Two different distributions in one. Now, that does not mean that potassium does not have variation between male and female. Actually, if you did a proper estimation of males and females, you get two curves or two distributions which do not exactly overlap. There is a difference between male and female potassium. The only difference is that the difference here is not statistically significant. That one for hemoglobin is statistically significant. There's a huge difference. Therefore, you need two reference intervals for the two groups. Now, when we look at lipids, and I think I mentioned that in that study we did, in that big class we had, if you go into the population, there is a statistically significant difference in lipids for every 10 years, for every decade. So for lipids, you cannot have that simple mean plus or minus 2 SD. What you would probably need to do is to partition the population based on age. 0 to 10, 10 to 20, 20 to 30, because there is statistically significant difference. Now, one of the problems with now this partitioning is about that overlap between ages, 0 to 9 or 9 or 10 to 19 or to 20. You are not exactly sure where the cutoff point is going to be. So it creates a challenge, but it's far much better than lumping the reference interval for lipids in one group. You have got to partition. The other partition criteria would be the ABO blood grouping, the HLA antigens. There are quite a number of these partition criteria, which is also called categorization or stratification. Now, let me again mention that Gaussianity is default in statistics. Default, like if you key in data onto your computer and there is power outage, the computer does not ask you, where do I save data? It will save default, and the default is the C drive. So if you're going to look for your data, you just go to the C drive. The same thing about statistics is that Gaussianity is default, and most of the assumptions are usually based on Gaussianity. Unfortunately, or fortunately, I don't know which is which, if you go out collecting data in the field, bring it back to the office or to wherever, 50% of the times your data will be Gaussian. 50% of the times your data is not going to be Gaussian. That which is not Gaussian is going to be skewed or is going to be chaotic. And because we need Gaussianity, because it's default in statistics, we try to transform data from non-Gaussianity to Gaussianity. Two ways of doing this is to use the square root, and the other one is to use logarithm. Fortunately for most of us who are not mathematically oriented, the square root is far much better than, or it's supposed to be more powerful, not better, than logarithm. So you can convert your data to their respective square roots, and then key in the mean in your Excel and ask for cumulative frequency distribution. And you're going to end up with a beautiful Gaussian curve or a bell-shaped curve, which is the normal distribution. Now, if data does not conform to Gaussianity, even after transformation, then you can use the so-called non-parametric statistics. Non-parametric statistics is usually simple. You just arrange your data in ascending or descending order. Then you look for the 2.5, 97.5 percentile. Now, for parametric statistics, it's either the F-test, we have seen that, and you can use the student's t-test. Now, when do you use these tests of significance? Let's go back to hemoglobin. You do the male-female hemoglobin, get the two different means, the two different variances between male and female, and then you compare them. So the F-test usually does the check, the check on precision, which is reproducibility. The t-test usually does bias and accuracy. So what you're trying to find out is, does the two populations belong to the same population? What you'll find with potassium is that they actually do, male, female. What you find in hemoglobin is that they don't overlap. Therefore, they are two different populations, and you have to end up with two different populations. So what you're actually doing is to test whether there is a difference between this population and this population, either based on age, based on the H, on the ABU blood grouping, or based on gender. And I think that is the end of my presentation. Like I said, it would have been best if we sat and exchanged ideas on this, but again, the circumstances are such that we have got to embrace what we have. It's not that I like talking. I've got to keep a glass of water next to me. So, any question on this? I know somewhere either Thursday or next Thursday or Friday, or Wednesday, we shall be having a case on lipid profile, and I think I'll send it to the class lab maybe 2 or so days before, so that you can actually go through it, and you can probably be able to ask a couple of questions as I continue talking. But it's all based on the lecture, the big lecture we had. Another question or any question or comment? I'll assume none is coming, therefore we can add the exercise.
Thank you, Dr. Maina, for your time today. If there's no questions from anyone, then I think we can end the session.
Thank you. You can actually do so.
Thank you. Have a good day, Dr. Maina, and everyone.
Okay, thank you.